Hey everyone, today we're looking at inverse functions, and what we're going to do is take a look at how to verify them as well as find them. Those are the two main skills. So just to start off with a general description, we can think of functions that undo each other are inverses of each other. And so we have this function notation with this, it looks like an exponent, right? But it's really not an exponent. It is just a superscript. It's a piece of text that's just pushed up to the top, right? And so when you are reading this, don't read it off as if we're an exponent. Read it as a function. So you would call this as f inverse. That's what you would want to say instead, f inverse of x. Don't say f to the minus 1 because that's how you might treat an exponent, and these are not exponents. So one way of introducing this is just to kind of remind you of some basic operations that undo each other. And you might remember things like addition and subtraction undo each other, right? So in this example here, whatever I'm starting off with, here I'm just using the variable. If I add 5 and then subtract 5, well, they undo each other, right? They are opposites of each other. We call those inverse operations. So if we can have inverse operations, then we can also have inverse functions that undo each other. You know, multiplication and division undo each other, right? The cubed and the cubed root undo each other. These are each pairs of inverse operations. And taking a little in the more advanced direction, if you have e to the power of x, a logarithm is the inverse of an exponential. Right? So in each of these cases, notice that you are finishing off with whatever you started with. And that's what this notation is trying to communicate here as well. If you take a function and you run the composition of that function with another function and your answer is just x, that means those functions undid each other. They canceled each other out. But you have to do it both ways. And if you get that same result of positive 1x every single time, then that's how you verify that you have a function. So here they're starting off this definition by saying, hey, there's just two different functions, but I'm discovering that when I run the composition both ways, I'm getting this answer. Therefore, it must be that these two are functions of each other. So under these conditions, that function that we had started off calling function g is in fact the inverse function of the original. So we could just use this notation. If you take a function and its inverse and you run the composition with them, they will undo each other and just leave you with just x. So not 2x, not 3x, not a negative x, just a positive 1x, and you have to get that both ways. So this is the first skill we're learning here today. This is called verifying an inverse. You could show this notation in either one of these two ways. They work and they communicate the same thing. Here we're starting off with the function, we plug in its inverse, we run the composition, and out comes this answer. So we already know what the answer is, so think of this more like a proof. When you are verifying something, you are proving that that is indeed the case. And we have to do it both ways. So algebraically, there's a few steps here. And that skill that we're learning about is not the same thing as finding an inverse. These are two different skills. Finding means I don't have the inverse and I need to find it. But verifying, like what you see here in example 1, verifying means we already have the two functions and we will show that they are inverses of each other. And we do this by running the composition both ways. So think of it more like a proof in the sense that you're just going through the technical skills of simplification to show that every pair of opposite operations will in fact cancel out between these two functions. So here we'll look at it algebraically and then graphically and then numerically. So here's the algebra part. So what we're doing is we're starting off with this first composition, f composed with g of x, starting off with the letter in front, the f of x function. And let me color code this. For my second function, I'll use my orange color here. That is going to be plugged in right there for the input. So we end up with 3 times my input cubed to the power of 1. And again, that input is cubed root of x minus 1 over 3. So now we have to keep in mind the correct sequence of steps in order to cancel out each pair of opposite operations. So we have the power of 3 cancels out with the index of 3. So that means we now have 3 times the fraction, x minus 1 over 3, with the plus 1 on the outside. And then 3 divided by 3 cancels out. That leaves me with x minus 1 plus 1. Of course, those constant terms cancel out. And there's my answer. That's exactly what we're looking for. You're looking for positive 1x. Now we have to do it both ways. So now here's the composition of G with F. All right, so this is my other color. This is my G of x, which is the cubed root of x minus 1 over 3. And so right here in place of x, we're going to do the substitution of the other function, 3x cubed plus 1. So I'm just using parentheses there to show where it's going to be dropped in. And again, the skill here is just making sure we are going through the right sequence of steps to see what cancels out. In the numerator of that fraction, the plus 1, minus 1, those constant terms cancel out. So we have the cubed root of now 3x cubed over 3. So now inside the radical, the 3 divided by 3 cancels out, and that leaves us with cubed root of x cubed. So finally those powers cancel out, the power with the index. And there's our result, positive 1x. You're looking for that same answer with both compositions. So that has now proven, that has now verified that these are functions of each other. So instead of calling this g of x, we could use the notation f inverse of x with that sign that is a superscript that looks like an exponent, but it's not an exponent. Let's see what's happening graphically and numerically. These kind of go hand in hand. In fact, it's probably easier to start here with numerically so we can then plot the points. So here's my original function. And here's my other function, which we now know is the inverse, but I'll just be consistent and call it g of x. And so let's just pick a few inputs here. Let's plug in -1, 0, and 1. That's really not enough to plot, but we'll kind of work with it. So plugging in a value of -1 for x, we're cubing that, multiplying by 3, adding 1, we get a result of -2. When we plug in 0, we get an output of 1, and when we plug in 1, we get an output of 4. So let's plot these on our grid. So we'll kind of do graphically and numerically at the same time. Now, with only 3 points, you might just think it's a straight line. It's not. The parent function is x cubed, so that's the very narrow and tall S-shaped curve that normally goes to the origin, but with the plus 1, it's been shifted up 1, and with a value of 3 in front as the multiplier, it's a vertical stretch of 3, so it's 3 times taller. So there's my original function. Now, to turn that into the inverse, one of the details, we didn't point this out on page 1, but going back to the previous page, one of the details is that everything switches in a very casual sense, switches. A point xy on the function now becomes y comma x on the inverse function. And so what that means is all of the inputs are now outputs. That means the domain and the range exchange places. So that's what we're going to see here with our table of values. What used to be the inputs are now going to be the outputs. So switch each ordered pair, exchanging the x with the y coordinate, and that's what we will plot on our graph. And when we plot this on our graph, again, it looks like you have 3 points in a line, but that's not in a line. Still that S-shaped curve. This time it's lying on its side, more like this. So what ends up happening is that result, graphically, is a reflection of the original function over a line with a slope of 1. So here this line has a slope of 1. It goes through the origin. And so you can think of this as your line of reflection. And so if you take the function and reflect it over this line of reflection, it ends up here. And that's what you see numerically in the table of values. All right, so now that's skill number 1. Here's skill number 2. You've probably done this before last year in your Algebra 2 class. Here we're finding the inverse algebraically. So we go through this sequence of steps. We're going to start off by replacing the original function notation with just the letter y. They both mean outputs. It's just easier to do the algebra with the y instead of the f of x. Then we're going to exchange x with y. And when we do that, that's when we're getting it ready to work with the inverse, because on our table you can see how we exchanged the x with the y values. Here we're exchanging inputs with outputs. Once we've done that exchange, we're then going to solve for y. And lastly, return it back into function notation by replacing that letter y with f inverse of x. All right, let's take a look at a few of these examples. Here's example number 2. First, replace that function notation with the y. Exchange x with y. So it looks like x equals 5y minus 7. Now we're going to solve for y. So adding 7 to both sides. And then lastly, dividing away the 5 to isolate the y. That's essentially it, but we don't like to leave it with a y representing the output. We want to replace that with f inverse, because that communicates it's the inverse of the original function. So here are just a few other variations on that idea. Here's number 3. F of x equals the square root of x minus 2. Replace the function notation with a y. Now exchange x with y. And now solve for y. So I'm going to undo the square root with the power of 2. So x squared equals y minus 2. Add 2 to both sides. And there it is. But we don't want to leave y as the output. We want to replace that with f inverse. And here's another one for good measure. Here in number 4 we have f of x equals 5 minus 3x over 2. So again, replace that function notation with a y. Exchange x with y. So it looks like x equals 5 minus 3y divided by 2, all divided by 2. Now let's solve for y. So multiply both sides by 2 to get rid of that denominator. And then subtract 5 for both sides. And here on this next step, we're dividing both sides by a negative 3. However, we don't want a negative in the denominator. We want a positive. So we can either take that negative and park it in front of the fraction, or we can distribute it to all terms in the numerator. And that's what I'm going to do. So I'm going to take the negative sign and distribute it to the top. So it's a negative 2x and a plus 5, all divided by 3. That's my f inverse. And that's it.